Hello and welcome back. In this video we are going to describe the combination of the type of main controller we discussed in our previous video, and also we are going to add the proportional, integral, derivative controller. And this is the main combination of all the main controller. PID, where it comprises of proportional, integral, and derivative controller all into a single controller. And firstly, we can look at what is a proportional integral controller. So we have proportional integral controller and how it is defined. And we can define a proportional integral controller, which is also known as PI controller. A proportional controller is defined as a controller which produces an output, which is the combination of the output of the proportional and integral controller. We define proportional controller, let's say MPT, which is the output of a proportional controller, such that it is proportional to the error signal ET, which is the input to the controller. And we simply removing the proportional sign by adding a constant. We have KP ET. And now this is our equation for proportional controller. And for the integral controller, we say that the output of MI, which is the output of the integral controller, is proportional to the integration of the input. And we can say the input is nothing but the error signal dt. And by removing the proportional sign, we now have MIT, which is equals to Ki integration of 0 to infinity, and we have ET dt. Now we are going to combine. When we talk about the combination, we are now referring to the addition of both of the signal. So if we now have to have our final proportional integral controller design by focusing on the response of this system, we now can say M PI T is equivalent to KP ET plus KI 0 to infinity ET dt. So this now represents the equation for the PI controller, and it shows the relationship between using the proportional controller and the integral controller. In our later video, I will explain how we can draw the block diagram representation of all of these controllers that we have discussed. And also you have to remember that all our discussion in this video is based on the time domain. Therefore, we are describing all this signal with respect to time. That's why we have T here. So a quick diagram, we can see that the input to the controller is nothing but the ET, and we have KP ET plus KI integral of 0 to infinity ET dt. And we can have only the output, which is the MPI T. So we want the output of the controller to control the plant. Therefore, any signal that is an input to a controller is known as the error signal. And I have made mention in a stable system, the error ET should be approximately 0 for a stable system. However, there are no complete stable system. We may have small error. However, we want to design any system that must reduce or minimize the error as much as possible. Therefore, the purpose of the controller is to minimize the error by producing a correcting signal such as the proportional integral controller output to control the specific plant, so that this plant must produce an output that will minimize the error. Larger the error in a system is not good. The error will lead to a system being in an unstable mode. Therefore, we need a controller design. So both the proportional and integral controller, they both take the same input, ET, which is the error signal. So you can see that for the proportional and integral controller, both of them are taking the same error signal as an input. And after processing the error signal independently, they are added together to produce the output signal that will control the plant or the actuator. In some other cases, the MPI, which is the output of the PI controller, can also be regarded as an actuating signal, and this actuating signal is responsible for actuating the plant. So in simple terms, we can say to control the plant. And we can look at the other controller, which is the proportional derivative controller. We can define what it is, and we can derive a mathematical equation that represents this type of controller. And we now have the proportional derivative controller. So I will write the definition, and it is called the PID controller in short. The definition for proportional derivative controller is such that it produces an output which is the combination of the output of proportional and the derivative controller. Or this controller is now producing an output which is the combination or the summation of the proportional and derivative controller output. Our previous video, we defined the proportional controller such that the equation is MPT is equals to KB ET. And for the derivative controller, we know that we have MD T is equals to KD D on DT ET. This is the equation of each of these controller. Now, for the PD controller, we can define the mathematical equation such that MPDT is equivalent to KP ET plus KD D on DT ET, and this represents the proportional, and this represents the derivative controller equation. So we can simply draw a block diagram. We have the input ET. Now to the controller we have KP ET plus KD D on DT ET. So this can be our equation, and the output of this block diagram can be MPDT. So those are just variables representing the signal into the system and the output of this system, and this system is known as the PD controller. Also, in our later video, we will also discuss the application and the usage of each of these controller, because in many special cases we normally select a type of controller that meets the demand of the control algorithm. We cannot use all these controller for a particular purpose. However, we normally choose the type of specific controller for a specific application, and we will also discuss some of the pros and cons of each of these controller and where you can use this controller to maximize the efficiency of your control system design. When we look at system stability, then it is important that you already know those time domain representation of each of these controller, because when we convert from time domain to frequency domain, especially in the Laplace transform, to analyze the system behavior and dynamics, we want to find the possible solution to minimize the error in a system. Now we will look at the Laplace transform. And before knowing those Laplace transform, it is important that you know the mathematical equation in the time domain. That is why I have explained most of this case scenario in the time domain. Finally, we are now looking at the proportional integral derivative controller, or the PID controller, which is the combination of the main and the initial combination of those type of controller. And PID is mostly used in most advanced control system design. So we can define our final control system discussion about the proportional integral and the derivative controller, and it is mostly written as a PID in short form. The PID controller is defined as the controller which produces an output that is the combination of the output of the proportional controller, integral controller, and the derivative controller. To summarize, we can say for the proportional controller, we previously said that MP T is equals to KP ET. By now we should be able to define each of these controller, and for the integral we can say MI is equals to KI, KP and KD. They are the constant gain of this controller, and the integration 0 to infinity, and we have ET, DT, and the final one is the derivative controller, where we have MD T is equals to KD D on DT ET. So those are our initial or the main controller. Now if we want to put all these controller together to form a PID controller, we have to sum up all of these controller together. So the final response or the output of the PID controller, we can say M PID T, which represent the final output signal of this controller, is equals to KP ET plus KI integral of ET dt, and we have the KD d on dt ET. So this is now our equation for the PID controller, and it is in the time domain. So we have the proportional, the integral, and the derivative controller. So simply in the block diagram, we know that all of these except the input, which is the error signal, and this controller is now summing up all this error signal with respect to each of the main controller. And we have the KP ET plus KI to ET dt, and plus KD d on dt ET, and we can have our response, which is represented by the variable M PID T. So this is our PID controller. The M PID is the final signal after summation of each of these main controller in a overall PID controller. Why PID controller is so special? In some control system design where we have a specific problem that this controller can be solved using a proportional controller, and maybe not the other controller. However, in some other system design, we might be having a controller that is consists of the integral controller, and maybe the derivative and the proportional controller may not be needed. And in some other circuit design where we might need a combination of two of these controller paired together in order to reduce the error that is produced in a signal. However, if you look at the PID, PID can be seen as a generalized controller because it consists of all the elements in the main controller that can be solved generally. Because if a system can use a proportional controller to reduce the error, then another system normally uses a derivative controller to reduce the error in the system dynamics. All of them together in a PID control system will greatly reduce the effect of producing an error, because the PID controller is now the combination of all this type of controller. That means it is more robust and it is mostly chosen in most of the advanced control system. And each of these controller, in our later discussion, we will see some of the features they normally impose to reduce the error, such as damping, overdamping, and the settling time. All of these consideration will come under each of these main controller and combining them into the PID controller. That means all of these features can be found and can be utilized in the PID controller. Therefore, it will mostly reduce most of the error in a control system design. And we will also look at the circuit configuration of each of these controller. And you might be wondering, why do we need to learn those controller? Is it only the mathematical equation that derives the signal, or it is some kind of system that we cannot physically see? Well, you might be able to learn from this video that this type of controller can be designed using physical electrical component, and this physical component can be used to alter the signal. In our system design discussion, we talk about a system, and this system can be derived from the initial component, such as the electrical component having values that can be able to manipulate the input signal and produce the output signal. Due to this manipulation of this system, it becomes more important that we can change the signal. If the input signal says that the error is too big, then the system, especially our controller, will have the ability to alter the signal output so that this output will control the actual output of the plant. Thank you for watching our video. Kindly subscribe to our channel and share this video with your friends so they can also be able to learn.